part 2 of my 3-part series on how to sketch a graph of a function without really using a graphing calculator, but instead using first and second derivatives. So on your screen right here you see a 4-term cubic polynomial, and our job of course is to come up with a sketch of this thing without using a calculator, and we want to do it pretty accurately. So we have a bunch of things sort of on our to-do list, and it all starts with finding out where the graph crosses the x and y axis. It's really important to find these x-intercepts. Right? If you're a little rusty on that, go check out my video. Next we'll do critical points. Also, that's a separate video, check it out. We'll talk about intervals of increasing and decreasing. You can find that in a different video as well. Concavity and inflection points are in other videos, and finally the extrema will be in a 6th and final video. So the video you're watching right now is basically a culmination of those 6 skills. So if you're a little rusty on those, or if you didn't watch them at all, well, you definitely want to watch those before you watch this one, because we're going to bring all those skills together with first derivatives, second derivatives, and all that stuff right now. So let's do this. Our job first is to find where the graph crosses the y-axis and the x-axis. So let's first change this to a function. Instead of f of x, let's use y. To find the y-intercept, you just basically get rid of all the x terms. It's that number at the end, -8. So this graph is going to cross the y-axis down here at -8. To find the x-axis, oops, let me undo that. To find the x-intercept, rather, you replace the y with 0, and you solve this thing. Now this is a cubic. A little bit trickier to solve cubics than it is to solve quadratics. So what I need to do is sort of look back into my bag of tricks and say, all right, I'm looking for roots. Roots, another way of saying find the zeros. Find the zeros, or find the solutions of the polynomial. Find out where it crosses the x-axis. In other words, when we set y equal to 0, that's really what we're doing. So we need to figure out these roots, or these zeros, the points where the graph crosses the x-axis. So we think about our rational root theorem, and again, I sound like a broken record, but again, this video is not really to address that skill. That has its own video. Check it out. So we're going to use the skill of finding rational roots of a cubic or any sort of polynomial. So the rule is basic. You take the first term, which is we'll call A, and the last term, which we'll call C, and the potential roots given by the little equation here, C over A. But we don't just want to take, that's not really our answer, -8, right? That's just sort of a pattern, and this doesn't really mean -8. It actually, we're talking about the factors of -8 and the factors of this bottom term. Thankfully it's just +1, so that's kind of nice. So all of the potential zeros, we're going to list the potential zeros, or the x-intercepts, is given by -8 over 1, but we need to figure out all the factors of -8. In other words, what numbers multiply together to get -8? Well, it's 1 times -8, or -1 times 8, 2 times -4, or -2 times 4. So those possibilities are going to be my numerator, and my denominator are all the numbers that multiply together to get 1, which is a nice small list, just one thing. So my potential zeros, or my x-intercepts, are, I'm going to take 1 from this list, C over A, so 1 over 1. Let me undo that. 1 over 1 negative 8 over 1, negative 1 over 1, 8 over 1. I'm pulling a number from here, dividing it by this. So I have 2 over 1, negative 4 over 1, negative 2 over 1, and finally 4 over 1. So again, it's x equals c over a. All the factors of 8 divided by all the factors of a. Let's clean this up. This is a little bit nightmarish, so let's clean this up. I've got positive 1 and negative 1. So I'll just write it like this, positive, negative 1. I've got negative 8 and positive 8. So I'll write it like this, positive, negative 8, positive, negative 2, positive, negative 4. So these are my potential x-intercepts. To figure out if they're actually intercepts, I need to just kind of maybe pick one and see if it divides out with a remainder of 0. And we'll do this synthetically. If you're a little rusty on your synthetic division, I'm not really going to spend too much time on it right here. Go back and check out my video. So let's try positive 1. We'll start there. I'm just literally just picking that one out of the blue. So I'm going to do positive 1. Does that divide into this 4-term polynomial? And we're going to do it synthetically. So pull down all of these coefficients. Just pull down all the coefficients. Bring the 1 down. 1 times 1 is 1. Add 1 times 6 is 6. Add 6 plus 2 is 8. 1 times 8 is 8. Add, you get 0. So our remainder is 0. That means that x equals 1 is a factor, or a x equals 1 is a root of this function because it divides out evenly with a remainder of 0. So I'm going to rewrite it like this. If this is positive 1, my factor is negative 1. And it leaves me with this as a remainder. So it's 1x squared. If I started with a 3, I'd put a 2 there now, plus 6x plus 8. Now I'm going to try to factor this. I can do the same thing. I can pick a random number here from my potential list and go, but let's see if we can factor this. It's a quadratic, so I like to see if I can factor now. So I've got x and x. I've got 4 and 2. I've got plus and plus. Thank goodness I can factor. I don't have to do that synthetic division anymore. So this is the equivalent right here. This is the equivalent of our original function. And this will give us our three zeros, or 3 x-intercepts. So we have x equals 1, x equals negative 4. I'm solving each of these separately. These are my 3 zeros. Alright, so finally, that was a little bit trickier than example 1. Positive 1, negative 4, and negative 2. Those are my 3 x-intercepts right here. Alright, so that takes care of this and this. Next we want to do critical points. Critical points. So let me erase this. If you need it back up on the screen, just rewind the video. To find critical points, we need to find our first derivative. If you're a little, I keep saying this, but if you're a little bit rusty on your derivative rules, this is not the video for you. Go back and get caught up. We're taking the 3, multiplying it by 1 to get this number, and then we're just reducing this by 1. 2 times 5 is 10. Reduce the exponent by 1. Oops. 2x differentiates into just 2, and the constant disappears. So there's our first derivative. To find critical points, as you remember, solve that, set it equal to 0. So 3x squared plus 10x plus 2 equals 0. Alright, and the reason we're setting equal to 0, of course, is because we're looking for where the graph sort of levels off. And we're looking for a max where our tangent line is horizontal. Or we're looking for a min where our tangent line is horizontal. Right? That's the whole point of this. So let's see if we can factor this. Can we factor this right here? 3x and x, 2 and 1, plus and plus. Check that. Don't think that works. So let's move the 2 and the 1. Plus and plus. Still doesn't work. Alright, so it's not factorable. That's not good. So we've got to go and do our quadratic formula. So this is really testing our algebra here. So A, B, and C, 3, 10, and 2 respectively. The quadratic formula says negative b, x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Let's solve it. We got negative x equals negative b, so negative 10 plus or minus the square root of 10 squared minus 4 times 3 times 2 all divided by 2 times 3. Simplify it. So give us two answers here. Let's simplify the radicand first. 100 minus, let's see, 24 over 6. Negative 10 plus or minus 76, square root of 76 over 6. Alright, so we have, let's see, the square root of 76. Square root of 76, interesting. So let's do this. Let's go negative 10 plus that over 6, and negative 10 minus that over 6. And at this point, I'm going to see if 76 has any perfect squares inside of it, and it does. Negative 10 plus, let's see, 76 is 4 times 19, 40 plus 36, yeah. So 4 is a perfect square, so I'd take that out, plus 2 radical 19 over 6. So I've got two branches going here. You got negative 10 minus 2 radical 19 over 6. So I'm going to simplify this. All right, we're really testing your algebra on this one. These three things can be cut in half. So negative 5 minus square root of 19 over 3. And I'll change this one to the same thing. Negative 5 plus the square root of 19 over 3. I think we're probably ready to go to our calculators. Not to graph it, but just to get that value. So I'm going to go negative 5 plus the square root of 19 all divided by 3. So I get negative 0.214. Negative 0.214. That's another one of our zeros. Let's see if that makes sense. Negative 0.214. And I don't think it does. Interesting. Alright, we'll see where we made a mistake. We'll come back to that. Let's do this one right here. Negative 5 minus square root of 19 over 3. Negative 5 minus square root of 19. I forgot a parenthesis here. So if I do that and then I divide that by 3, let's see what that gets me. Negative 3.12. Negative 3.12. Let's see if that makes sense. No, that doesn't make sense either. So I made a mistake somewhere. Alright, I'm going to pause this and figure out what I did wrong. And when I figure it out, I'll press record again. Well, it took me about 3 seconds to figure out my mistake. In fact, I didn't make one. My mistake was that I lost track of what I was actually doing. I did the right math, and those two answers right there are not x-intercepts, but actually they are critical points, potential critical points anyway. I already found my x and y intercepts, so I'm on the critical points. Goodness gracious. You can see how quickly you can kind of get off track here and kind of lose your mind a little bit. So I've got negative 3.12. I'm doing my little number line thing. Doing a first derivative test, and these are my potential critical points. So I've got to see what my derivative is doing. I've got to see what my derivative is doing is to the left of this number, in between these two numbers, and to the right of this number. So let's do that. Let's see. Let's go back and grab our derivative again. Our derivative was 3x squared plus 10x plus 2. All right, we're going to get back on track here. These problems take a while. All right, let's pick a number to the left of negative 3.12. Let's try negative 4. So this is our derivative. We're testing negative 4 in here. So 3 times 16 minus 40 plus 2. That's, let's see, 48, 30 plus 18. Yep, 48 minus 40 plus 2. So that's 8 plus 2. That's a plus. That's a positive number. That means my graph is going up. Okay. Now we want to test a number in between these two, in between negative 3.12 and negative 0.214. I'm gonna probably keep it simple and test negative 1. All right. My mind is a little bit fried right now, so let's keep it as simple as we can. This is like my 10th video that I recorded today, so a little tired. Negative 1, let's test it in here. 3 minus 10 plus 2. So that's minus, let's see, 7 plus 2, that's negative 5. Graph goes downhill. Alright, so I've got myself, when it goes from up to down, I've got myself a maximum right here. Cool. Let's check a number over here to the right of negative 0.214. Mercifully, let's test 0. 0 goes right here, and here I get a positive 2. That's a positive. My graph goes back up right there. So that means when it goes from decreasing to increasing, I've got a minimum. So this is an increasing, and then it decreases, and then it goes back up to increasing. Alright, so I've got a minimum and a maximum. Cool. My maximum is at negative 3.12. Negative 3.12. Alright. So I need to figure out my y value when my x value is negative 3.12. So right there. I need to know how far up it is. It's up here somewhere. I need to figure out where. And similarly, I need to know how far down at negative 0.214, which would be like right in here somewhere. It's got to be down here. I got to figure those out. And to save time here, I'm going to actually go to my calculator for that. I'm not going to sketch the graph of this. All I'm going to do is type in the function. Type in my function here. So clear that out. I'm not going to, oops. I'm not going to cheat and look at the graph, promise. All I'm going to do is figure out this function value. So I'm going to go back to my home screen. I've got it plugged in there into y sub 1. I'm going to go to variables, y variables, function, enter, enter twice. In parentheses, I want to know the y value when x is negative 3.12. Negative 3.12. 4.06. Alright, so my maximum is negative 3.12, comma 4.06. All right, we're on our way here. So negative 3.12, comma 4.06. Right here is my max value. Similarly, I want to find my minimum value when x is negative 0.214. So I'll do the same thing, except this time I'm going to plug in negative 0.214. Enter. Negative 8.21. Okay. So I was right about that one. I thought that it was going to be way down here, and it is. So negative 0.2, this is negative 0.5, negative 0.25. So it's in here and then way down here. That's my minimum value. Okay. So I'm going to get this guy. Remember, this is my y-intercept. And I've got my minimum value. All right. We're moving right along here. This is taking a little bit of time. I didn't think it was going to be this challenging because there's a lot of algebra involved, including quadratic formula and rational root theorem. But I've taken care of my critical points. Got my max and my min. My increasing interval, of course, is going to be everything that's in red. So negative infinity to negative 3.12 is increasing, and it also increases from negative 0.214 to forever. So that's increasing. This function decreases where it's purple there. So decreasing interval from negative 3.12 to negative 0.214. So that's taken care of. Boom and boom. Inflection point. All right. Inflection point is going to be, we got our max and our min too. Cool. So we just need to do a second derivative. These are all relying on our second derivative. So let's go back over here to the right. We're going to erase some of this stuff that we don't need anymore. I'm going to keep my first derivative there. Remember, that's my first derivative. To talk about concavity and inflection, we just want to find our second derivative. So it's 6x plus 10. Set that equal to 0 and solve it. So negative 10 over 6, negative 5 over 3. Negative 5 over 3, we're going to do a second derivative test and compare that to how that graph would actually look. So we're going to test a number to the left of negative 5 over 3 in our function. Negative 5 over 3 is negative 1.6, so let's check negative 2. Check negative 2 in your second derivative. 6 times negative 2 plus 10 is negative. Negative second derivative means concave down. Concave down. Check a number over here bigger than negative 5 over 3. Let's check 0. 6 times 0 plus 10 is positive. Cool. Positive means concave up. When the concavity changes from down to up, that is called, of course, an inflection point. Inflection point is where it changes from down to up. In terms of the intervals of concavity, it is concave down from negative infinity to negative 5 over 3, and it's concave up from negative 5 over 3 to infinity. Sweet. And the inflection point is when x is negative 5 over 3. I'm also going to figure out where that, I'm going to plug that into my function to get the actual value. So I'm going to enter that in again. I want to get the exact y value. Negative 5 divided by 3. This will give me the y value of my inflection point, negative 2.07. Negative 2.07. So my inflection point is negative 5/3, negative 2.07. Alright, so let's put that on the graph too. I'll put that in red. This is where my graph changes from concave down to concave up. Negative 5 over 3 is negative 1.6. and then we're going -2 basically. So -1.6 is right here, and then down to -2. So right in there is my inflection point. All right, we've got everything we need now. So finally, mercifully, after about 25 minutes, we can graph this function. I've got concavity from the left of this is concave down. So I'm going to go ahead and graph this one. Something like that. And then the concavity switches, and it goes down to this minimum value, goes through the y-intercept, and comes back up. So there we go. That is how the graph looks, using all of our first and second derivative tests, including some algebra 2 thrown in there. So here's the final sort of test to see how we did. Let's see if I can bring the sketch of the graph up here and compare it next to the one that we just drew. I have it down here hidden. Let's bring it up. Hopefully this is the same. If not, then I might just delete this thing and start over. I think we did fine though. Yeah, let me move this out of here too. So do they look alike? Let's see, we go up here and we see that our maximum looks perfect. We see that our 3 roots, our x-intercepts are perfect. We see that our minimum is slightly to the left of our y-intercept, so that looks perfect. And it looks like our inflection point is somewhere in there as well. So I think we did all right for ourselves. Just took a while. A lot of algebra 2, a lot of course, algebra, but a ton of calculus. So these are important skills. Knowing how to do that is something that you'll definitely be required in the first couple weeks or couple months of calc. So I hope this helped. I'm probably going to do example 3 tomorrow because I'm exhausted, but I hope you enjoyed this, and apologize about the length of this one, but you got a lot out of it, I'm sure. A lot of first derivative, second derivative stuff, and look forward to example 3. And as always, please subscribe and comment if you have any questions. Okay, thanks for watching. Bye.